Okay, Unit 5, Chapter 22, one sample t-test and one sample t-interval. At the end, I'm going to do the example that's in your notes, which is the coffee cup example and the battery example. All right, so we left off where we had sampling distributions and a one prop a one prop z-test and a one prop z-interval. So remember my P from phantoms meant parameter. And my parameter that we used was P, my proportion was P hat, and my standard deviation was square root of PQ over N. And we had a normal model where the mean was P and the standard deviation was PQ over N. And you found a z-score. And with the z-score, you found P hat minus P over square root of PQ over N for the one prop and then the two prop you had. And it was all around P and Q. Well, now we are going to be doing sample means, and the parameter now is going to be mu, not P. Before, remember, I had the true proportion, and now I'm going to have the true mean. And so now my standard deviation is going to be standard deviation over square root of N. But I have a small problem. I have a problem because I can't do standard deviation because I don't know it. So I'm going to use S, which is my sample standard deviation. But the problem is I can't do a normal model. So I do something that's similar to a normal model, and that's called my T distribution. And I'll tell you in just a second, but it's T degrees of freedom is my normal model. I have it down here already, but you're going to see the normal distribution and the T distribution. I just want you to notice that the T distribution is much shorter and the tails are fatter than the normal distribution. You can see the normal distribution isn't quite like that. In fact, if I were going to actually draw out the normal distribution, remember at 1, 2, 3, I'm pretty much at the end of the normal distribution because 3 standard deviation is 99.7% of the curve. But you see with the T distribution, this purple one sticking out, that it keeps going, -4, -5, and you're going to see that it's affected by its sample size, where the normal model is not. All right, so because I can't use the normal model, remember the normal model found my z-score, I'm going to do something called my t-score. And my t model is going to replace my z. So if you read through the notes, that's exactly what this says, exactly what I just told you, that the approximate normal with mu and the standard deviation of sigma over square root of n. But it's unknown, this is the problem, and so we can't calculate the standard deviation model. And so that tells you we're going to use S instead of sigma. And so my standard error is S over square root of n. If I were standardizing the normal model, I'd use Z equals X bar minus mu, because this is, remember, parameter minus, I got it that backwards, statistic minus parameter over standard deviation, which I've always told you observed minus mean divided by standard deviation. Well, since I'm not able to use sigma, I am going to use S. And I can't use Z, as I told you, we're going to be using our T distribution. Okay, so I want to show you with here, if we had a game and I have 3 people, and I tell you, I want you to choose any number in the world, any number you want to. But the key is that I want it to total to 100. So if the first person says 50, and let's say the next person said 100, then the third person would absolutely have to say 100 plus 50 is 150, would have to say -50, because I told you that you can choose any ones in the world, but the sum has to be 100. So I had 3 numbers chosen, but one of the ones that I chose was forced. And so I only had 2 that had a degree of freedom to choose. So if I were trying to tell you what degrees of freedom does my T distribution have, that's exactly what it would be. It'd be n minus 1. And I want you to show your work when you do this, because then it demonstrates that you understand how to get the degrees of freedom. Most of the time, the calculator will give you the degrees of freedom, but you need to make sure you put how you're getting the degrees of freedom, because there's going to be different tests that some degrees of freedom are n-1, others are different ways of finding it. So I want you to make sure you show it. All right, so if I were, let's track back to our z-star for a 95% confidence interval. Let's review how I find that. Remember, the center 95% is here, and I'm wanting this value. If I put it in inverse norm, I look up my area, and area I'd have to put 0.975. Remember, because 95% is just that area there, and my calculator starts here. And since my calculator starts here, if I ask for 95%, it's only going to give me up to here. It's not going to go all the way to where I want, so I have to have that extra 2.5%. So I'd put area 0.975 for inverse norm. And if I put that in, my mean and standard deviation are 0 and 1 because it's a normal model, I would get 1.96 for my z-score for 95% for z-star. So I want you to find now the t-star. Okay? So t-star for 95% confidence interval, you're going to still put in 95%. So please bring up your calculator. And go to statistics, distributions, and we're instead of inverse norm, we're going to go to inverse t because I'm going to do it for the t model. So the area, I'm going to put 0.975. The degrees of freedom, I'm going to let you investigate. Let's go to 10. Now let's change it to 100. And now let's change it to 1,000. If you notice, as it gets bigger, it gets closer and closer to that 1.96. Keep going, right? All right. I'll keep going to 10,000. But I have just given you an approximation. Keep going bigger and bigger. Let's see what the actual inverse norm was. Inverse norm, remember, 0.975. Really, really close to it. So as the sample gets bigger, you can see that this number gets closer and closer to what my z-score would be. So my t-star gets closer to the z-star. So what that means is as the degree of freedom increases, that means I get a bigger sample size. It gets closer to normal because S gets closer to sigma. All right, this here is my confidence interval because let's look at it. I've got X bar is my statistic plus or minus my critical value over my standard error. Let's jump to our formula chart. You could check out our formula chart on the second page. It's the second page here, and this is in the middle. So what I have written here, you can see, is the formula of my t-star. This first part here you can see is X minus mu. X minus mu over, there's divided by my standard deviation of f over square root of n, s over square root of n, excuse me. And for my confidence interval, remember, confidence interval is right here. Statistic, which is X bar, plus or minus critical value. It's a t distribution, so we're doing t star, times square standard deviation. So I have the same thing is X bar plus or minus my t star times my standard deviation. All right. Oh, excuse me. Remember that the t-table uses the area to the right, so let's go back, to the t-table one more time, and you can see the t-table. How do you know it's the t-star? Because it says it right there. If I wanted you to find the t-star degrees of freedom for 10, then let's go ahead and look at 10 right here. And let's do it for a 95% confidence interval like we were just doing before. Remember, 95%, means this outside here is 2.5%. And remember, the T-star's graph starts from here and goes in this way. So I'm looking for 2.5%. And this here is 2.5%. So if you look here, that's 2.28 at degrees of freedom of 10. And if you remember back in our calculator, you can see that top one, 2.228, that's what it was for my calculator. If you go down here to still at 2.5% on the same column, 100 is this one here. 1.984. 1,000 is 1.962. Infinity is 1.96. And you can see that's indeed a 95% confidence interval. So that confirms it as well. Okay, so once the T procedures are exactly correct when population is normal, one sample T procedures are exactly correct only when the population is normal. It must be reasonable to assume that the population is approximately normal to justify using the T procedure. So I need approximately normal. So that's exactly what we're going to say. So the T procedures are strongly influenced by outliers, so we're going to check the data first. We know when n is greater than or equal to 30, we're fine. I know this says 40, but I'm going to change it to 30 because you can use 30 as well. By the CLT, which is called the central limit theorem. That tells us that our data is approximately normal. And therefore, I can proceed to the T procedures. However, this first one is a small set of data, and the next one's medium. And honestly, if you just say if it's less than 30, you don't have to name if it's small or medium. You can just say that I'm going to need it to be approximately normal, which is unimodal, symmetric, and no outliers. If the sample size is at least 30, you can use the T procedures even if the data is skewed. So the first thing I'm going to do is going to give you, go ahead, and we're going to try a phantoms. By the way, let me just say one more thing. For RILT, random sample or random assignment, independent, large sample size, this is the large sample size, and 10% rule. For the other ones here, they're exactly the same as we've been doing the past few weeks. For large sample size, instead of NP and Q, right? We used to have NP and Q greater than 10. Well, guys, I don't have any P because remember the P stands for proportion. And this is means. This is doing the means. And so there's no proportion here. It's just doing the averages. So let's go ahead and look at here. A coffee vending machine dispenses into a paper cup. You get a 10 ounce of coffee, but the amounts vary slightly from cup to cup. Here are the amounts measured in a random sample of 20 cups. Is there evidence that the machine is shortchanging customers? Okay, let's go through this information before we start our test. Okay, 10 ounces is my mu. That's what's going to be my HO. Mu is equal to 10. Because that's what's believed to always be true about the coffee cups. The next one, I have random sample. 20 cups is my N. So I have a small sample, I have a medium sample size right here. So I'm going to have to go ahead and graph this data. And then I didn't show you, you're supposed to put a model here. So let's say that's 2.1 to 7.2. And let's say the number of siblings, average number of siblings in each class, in each family. So you would have to show this and say, okay, it's normal, unimodal, symmetric, no outliers, and then proceed. So that's what we're going to have to do here. We're going to have to graph this. So go ahead and put this into your calculator, and we're going to graph it. All right, so, and then next, is there evidence lets me know that I need to run a test, that's run a hypothesis test, and shortchanging, that just means my HA is going to be mu is less than 10. All right? So, so let's start with our phantoms. P is, I like to say the true mean because it's the population mean, but this is not too bad. The mean amount of coffee per cup. I really like to be a little bit more specific of this certain coffee vending machine because it's not every single coffee vending machine. Okay? Ho, mu is equal to 10. Ha, mu is less than 10. Okay, let's look at our conditions. Random sample, n is equal to 20. And what they did is they went ahead and graphed this. And so I'm going to graph it for you. All right, and they found it's unimodal symmetric. So they showed in a box plot and a histogram because a histogram is sufficient because that shows unimodal and symmetric. Okay, so let's go ahead and graph it. To graph it, I went ahead and put the data in, if I can, here we go. All right, so I went ahead, I know here you see the data. You can definitely just put it all in as 20 pieces of data. I put it as 2 columns and I said, oh, I have 5 pieces of data. I have 5 pieces of data that are 9.9. I have 2 pieces of data that are 9.7, 3 that are 10, and so forth and so on. All right, so now we're gonna do a data statistics, and I'm going to do histogram. There's my histogram. Now, I don't want spaces in between it. You can, without doing what I'm about to do, you guys can just push them together on your graph. But if you really want to change it, you can change this to plot properties, histogram properties, bin settings, equal bin width, and you can see there's a gap. So I'm just gonna double it to 0.1, and that will do it for me. And if you want to go to actions, Windows zoom data, it gets it perfectly for you. So you're gonna graph this and see that's exactly what they did here. Now the one thing that you need to make sure you do is put, it was 9 point, I think 6 was the lowest, and then 10.3. Of course 10.2 is here, and then this is ounces of coffee. Okay, so you just have to show that, look, remember, n greater than 30 guarantees that it's a normal model or approximately normal. So since it's less than 30, I need to show that my data is approximately normal so that I can continue. Okay, so next what you're going to do, it says, okay, we can conduct a 1 sample t-test with degrees of freedom of 19. Remember, that's degrees of freedom is my size is 20 minus 1 is 19. So the next one, the test statistic, is x bar minus s over s squared over n. And how you get your data is you can do the 1 variable statistics, or let's go ahead and I'm going to show you a 1 sample t-test on the calculator. You definitely could go ahead and find the mean and standard deviation of all of this, but let's just do the 1 sample t-test and get it for you. So I'm going to go back to our data, and I'm going to go ahead and run it. So it's going to go menu, stat, test, t-test, and I have data, so I'm going to use my data. If I didn't, I could go to statistics and I would just put it in. So I would just go to statistics if I didn't have my data, but I have a list of data, so I'm going to use my list of data. So my mu naught, that's the hose mu, is 10. My list, I called it coffee. And then because I did a frequency list, I have to go to that and go to data coffee. And I used a less than. Now guys, if you just did one gigantic list and you didn't do the 2 lists like I did, you would, on the frequency list, you would not touch it. You would just leave it alone. It already has a little number there, just leave it alone. Okay, I'm gonna go ahead and shade it so I can see everything. And this gives me my data. So if you see it, there's my X bar at 9.845. My T is negative 3.49. So now I can just fill in all of this here. You do not need this formula. In fact, I don't necessarily want you to use that formula on the test, because if you put S instead of sigma, et cetera, you'll get it. You get points off. I do want you to put this formula in with the numbers. All right, and then so you'll draw it. And this here, instead of the normal model, remember we had N01. This is not a normal model though, so we can't do that. So now you have T and the degrees of freedom was right there. and then you'll draw it, and it's negative. I put the 0 here. It's negative 3.501. You draw it, and that is still my p-value. So you're going to write to p-value is there. And the p-value, everything was already on my calculator. My p-value was 0.001. If you put this TCDF, this means absolutely nothing because there's nothing labeled. And I didn't use TCDF because you could use TCDF where you could be, basically that's negative infinity, the negative 3.51 to 19 that gave me here. I used the one sample t-test and I got all of my data. All right, and so see, this is showing the probability that X is less than that 9.845 is the same as my probability that my T is less than negative 3.501. So it's just converting it to a standardized test statistic right here. All right, same conclusion. Since P is low, we're going to reject HO, and this gives you a really nice conclusion. If the true mean amount of coffee per cup were 10 ounces, we'd expect a sample result. This is the definition of p-value, guys, by the way. This is p-value definition, all right, which you do not have to have in your conclusion, but you are asked about p-value definition a lot. We'd expect a sample result at least as extreme as the one we observed in about 1 out of every 1,000, because that's my p-value, samples due to chance. So now this is what you do need. This is strong evidence to conclude that the machine is shortchanging the customers. The reason it's strong evidence is because 1 out of every 1,000 by chance, that's very rare. All right, and that is your phantoms. Okay, here's an example of panic. So when do you use phantoms? You use phantoms whenever you're running a test. If it says, is there evidence? When do you use panic? You use panic whenever you're doing an interval. How do I know I'm doing an interval? It literally will tell you to do an interval. Okay, it will always tell you to do an interval, and that's how you know you need to do an interval. Okay, a company has set a goal of developing battery that lasts 5 hours in continuous use. In a first test of these batteries, it has this lifespan, and these here are the lifespan that you're going to do. All right, so the first thing you're going to do is you're going to define it. Again, I like to put the true mean lifespan of battery in minutes. And so now you're going to do your conditions. Now notice there's no independent, you don't really have to show independent for means, but I always use RILT just because it's easy to remember. Random, independent, and notice because this is 11, it's a small sample, I have to show there are no outliers, approximately symmetric, approximately normal. And so you're going to do the same thing. I'm going to put these in here, and then we're going to graph it. And then you're going to graph it with a histogram the way I just showed you on the previous one. So let's go ahead and do that. So I have 321, 295, 332. Actually, let me see if I can do this and just do a split screen. Okay, didn't work. It's not wanting to split. Okay, so 321, 295, 332, 351. Okay, so let's start a new graph. So 321, oh, okay. Batteries here, and then I've got 321, let's see, 295, 332, 351. $336, $311, $253. $270, $326, $311, $288. I missed one. I know I did. I missed that one, 326. Okay. All right, so I've got them all in here. And I'm going to graph them. Data statistics, graph, batteries. There we go. And you can see plot type, box plot. You can see there's no outliers, histogram. So now you can see the data and you kind of make like, ooh, it kind of looks ugly, skewed. Okay, well, look, let's just, don't worry about it. Let's just fix it. Plot properties, histogram properties, bin settings, equal bin width. Let's change our width to 20. See how that does it. Let's change it one more time. Equal bin width. Let's change it to 25. There we go. Maybe even one more time. There. Okay, now go to back here. Windows zoom, zoom data. There we go. All right, so we have a slight, it's not perfect for sure, but it's fairly symmetric, you know, it's not terrible. There's no strong skewness though. That's the main thing that we're looking for. If you notice here, I do have some that's one way, but it's not really a strong skewness. So you can go back here and you can look at your plot type and go to box plot. And you can see, I definitely have a skewness, but I don't have a terribly strong skewness where it's one way versus the other. So you can have, so that's why we put approximately symmetric, no outliers. So that sample that I did is just fine. Okay, and then random, independent, large sample size, and 10% rule. So now the 10% rule is, 10n greater than, the way that they showed is a little different than I show it, but same idea. So n is we may construct a one sample t interval with 10 degrees of freedom. How do we get 10 degrees of freedom? Degrees of freedom is 11 minus 1 is 10. All right, and so now a confidence interval, x bar, well, you can go ahead and look what your x bar is by finding the average of this in a one variable statistic, finding your t star and everything. But let's go ahead and run a confidence interval. So I'm going to just go ahead and do that. I'm going to run a confidence interval by going menu, stat, confidence interval, and it is a t interval, and I have data again. So my list of data is batteries, and I don't have a frequency list this time. My confidence level, I think they want 90%. Yes, 90%. So I'm going to go to here, 90%, okay. And there we go. So I have 280, 8.84 to 321.706. My X bar is 301. My margin of error and my standard deviation is 37.39. And my N is 11. So it gave me everything except this value right here. And that value is my T star degrees of freedom 10. So I would have to go, remember, it's the middle 90%. And so I would need that extra 5%. So I would inverse T, and I'd have to put in 0.95 for 90%. So we're going to go do that. Menu, stat, distribution, inverse T, areas 0.975, and degrees of freedom is 10. And there's that 2.228 that we were looking at. So, oh, wait, hold on. Did I mess something up? Oh, I did 975. I'm sorry. 0.95. There we go. 1.812. There we go. Now it matches up. Okay. So on your test, you're going to need it to look exactly like this, but you are more than welcome to, of course, use all of the technology that I used in solving this problem. Okay. Thank you very much, and we'll continue this. Oh, and your conclusion. I apologize. Conclusion. We are 90% confident that the mean battery lifespan is between 292 and 325 minutes. It's right here. We rounded here. You could round if you want. You don't have to, because 90% of the sample sizes will produce a sample mean within 16.2 minutes of the true mean. How'd they get 16.2 minutes, by the way? I'll show you how. This here is 16.2. And look, let me show you here. If you look in the margin of error, oh boy, 16.2. Oh, no, that's not, I read that wrong. 16.2 minutes is this, is within 16.2 of the true mean, because what it's saying here is if I take 324, 0.7 minus 292.4 divided by 2, that's going to be, which I have mine that came out to 20, so I must have done something. You know what? I did a 90% confidence. Yeah, that should say, so that's wrong. That should say that 20, not within 20 of the true mean. Yeah, that's a mistake here. So I'm just looking at here. My margin of error is 20.4. So that's exactly what it should say is 20.4, not 16.2. Right there. Okay. All right, I hope this helped. Thank you.